This video explores the topic of predictive maintenance within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. In this short clip, we will explore the importance, key principles, and techniques of predictive maintenance in industry, with a special focus on vibration-based approaches. There are three main maintenance strategies used for industrial machines. The first is run to break, where a machine operates until failure occurs. This maximizes operating time, but failures can be catastrophic, leading to severe machine damage, safety risks, long production downtime, and very high repair costs. The second strategy is preventative maintenance, which is performed at fixed-time intervals, often much earlier than actually needed. While it is easy to plan and reduce the risk of sudden failure, it often results in unnecessary repairs, premature replacement of components, and increased costs. The third strategy is predictive maintenance, which relies on continuous monitoring of machines using sensors and advanced analysis of the collected data to detect defects early and predict potential failures before they occur. Maintenance is performed only when necessary, preventing failures while avoiding unnecessary replacement of functional components. Predictive maintenance aligns with the principles of Industry 4.0 and 5.0 and smart manufacturing, significantly contributing to cost savings, reliability, and efficiency. Several techniques are used for machine condition monitoring and fault detection, including vibration analysis, lubricating oil analysis, acoustic noise analysis, high-frequency ultrasound emission, performance analysis, and thermography. Among these, vibration analysis is the most widely used, enabling defect detection at very early stages. Machines generate characteristic vibration patterns during both normal operation and faulty conditions. Each machine has a unique vibration signature related to periodic processes, such as shaft rotation, gear meshing, bearing motion, and electromagnetic field rotation. These processes appear at specific frequencies in the vibration spectrum, allowing the vibration source to be identified. Vibrations are typically measured using accelerometers mounted on the machine's surface. Results of vibration analysis are available almost immediately. Thanks to extensive practical experience and advanced analysis tools, vibration analysis is the dominant technique in modern predictive maintenance. The next diagnostic technique is lubricating oil analysis. As defects develop, friction and wear increase, producing microscopic particles, typically up to about 10 microns, that accumulate in the lubricant and are collected by filters. By analyzing the amount, type, shape, and size of these particles, it is possible to detect the presence and type of a defect. Compared to vibration analysis, oil analysis is slower, usually requiring several days of laboratory processing, and it often cannot precisely locate the faulty component. For example, if several bearings are made of the same material, oil analysis can indicate that a bearing is failing, but not which one. Vibration analysis, in contrast, can localize the fault based on characteristic vibration patterns. Therefore, vibration analysis provides higher diagnostic capability, while oil analysis serves as a valuable complementary method. Another important technique is acoustic noise analysis, where machine noise is recorded using microphones placed at a distance. Unlike vibration sensors, microphones enable remote measurements, which is useful in harsh environments, with extreme temperatures, high pressure, humidity, or aggressive chemicals. However, vibration analysis is more sensitive and can detect earlier stage faults, while acoustic analysis is typically effective for more advanced defects and is also susceptible to ambient environmental sounds, which can reduce diagnostic accuracy. A relatively new method is high-frequency ultrasound emission analysis. Defect initiation and crack growth generate high-frequency mechanical waves, typically in the range of 100 kHz to 1 MHz or higher. These waves are detected by piezoelectric sensors mounted directly on the machine surface and cannot be measured remotely. The main advantage of this technique is its ability to detect very early-stage defects, often earlier than vibration analysis. Its main limitation is the need to measure very high frequencies. Performance analysis and the identification of performance degradation represent an important diagnostic approach, as they can provide clear indications of specific faults. Thermography is a non-contact technique used to measure temperature distribution in machinery. Local temperature increases indicate higher friction and wear, suggesting developing defects. While its main advantage is non-contact measurement, thermography typically detects faults at later stages, which limits the time available for maintenance planning. In practice, a significant time passes between the initial formation of a defect, such as a microcrack, and catastrophic failure. This gradual progression allows defects to be detected and repaired before failure occurs. The figure illustrates this progression and shows when different diagnostic methods are able to detect the fault. The primary goal of condition monitoring is early defect detection, providing sufficient time to plan maintenance, reduce repair costs, and minimize downtime. Among available techniques, high-frequency ultrasound emission and vibration analysis enable the earliest detection, allowing timely repairs and component replacement. Vibration measurement and analysis is one of the most widely used techniques for predictive maintenance. Vibrations are oscillatory motions around an equilibrium position and are described by displacement, velocity, and acceleration. These quantities are closely related. Velocity is the derivative of displacement, and acceleration is the derivative of velocity. The amplitudes of these quantities depend on frequency. At very low frequencies, displacement amplitude is dominant. For mid-frequencies, velocity amplitude is dominant, while at higher frequencies, acceleration amplitude dominates. However, modern wideband accelerometers cover a very broad frequency range, from about 0.5 Hz to over 20 kHz, allowing acceleration to be measured even at low and medium frequencies. Although displacement, velocity, and acceleration can theoretically be obtained from one another, in practice, integration is much easier than differentiation. Differentiation amplifies noise, while integration reduces it. As shown in the figure, differentiating a noisy signal distorts it, whereas integrating it produces a clear sinusoid. Therefore, velocity and displacement are most reliably obtained by integrating acceleration. As a result, vibrations across all frequency ranges are now predominantly measured using accelerometers, making acceleration the fundamental quantity in vibration analysis. Accelerometers are sensors used to measure acceleration. An accelerometer consists of an inertial mass coupled to a sensitive element such as a piezoelectric crystal or a capacitive structure. When the system accelerates, a force acts on the inertial mass according to Newton's second law and causes the mass to act on the sensitive element, generating an output signal. In piezoelectric accelerometers, this output is an electric charge, while in capacitive accelerometers, it is a change in capacitance. Since the force is proportional to acceleration, the output signal is also proportional to acceleration. The sensitivity of an accelerometer depends on the inertial mass. A larger mass produces a greater force for the same acceleration, and therefore a higher output signal. The two main types of accelerometers are piezoelectric and MEMS accelerometers. Traditional piezoelectric accelerometers have been used for decades. They offer excellent performance, including high accuracy, high sensitivity, and a very wide frequency range, allowing them to capture high-frequency vibrations, which is very important for predictive maintenance. MEMS accelerometers, in contrast, are a newer but rapidly evolving technology. They are increasingly used in predictive maintenance due to their very low cost and small size. In addition, MEMS accelerometers allow for on-chip integration with electronics. Although their performance is lower than that of piezoelectric sensors, it is adequate for most practical applications. Recent advances in predictive maintenance have been driven mainly by the development of sensors, especially low-cost MEMS accelerometers, and by improvements in sensor data processing algorithms. Vibration signals can be analyzed using several techniques, including time domain analysis, frequency domain analysis based on fast Fourier transform, and time-frequency analysis such as wavelets and spectrograms, which provide a two-dimensional representation combining time and frequency information. In addition, specialized methods are often used, such as envelope spectrum analysis for high-frequency vibrations, cepstrum analysis for identifying harmonic families, and kurtosis for evaluating the statistical characteristics of vibration signals. More recently, the application of AI and machine learning models, particularly deep neural networks, has significantly expanded the capabilities and practical use of predictive maintenance. These techniques can also be used to analyze audio signals in audio-based predictive maintenance. Frequency domain analysis, based on the vibration spectrum obtained using the FFT, is one of the most widely used techniques in vibration analysis. In the vibration spectrum, 3 frequency regions can be identified. The low-frequency region contains components related to shaft rotation and defects, such as unbalance, misalignment, or shaft bending. The high-frequency region is particularly important because it enables early detection of bearing and gear defects. The mid-frequency region contains components at characteristic bearing and gear frequencies and their harmonics, often accompanied by modulation sidebands, indicating more advanced bearing and gear damage. The first image shows the vibration spectrum of a rotating system without defects. The second image presents a vibration spectrum containing low-frequency components, which indicate the presence of unbalance, shaft bending, or misalignment, but without any bearing or gear defects. The last three images illustrate how the vibration spectrum changes when bearing or gear defects occur. The third image represents the earliest stage of such defects, where a high-frequency haystack appears in the spectrum as the first indicator of defects. The fourth and fifth images show vibration spectra corresponding to more advanced bearing defects. The fourth image represents a defect on the outer ring, while the fifth image illustrates a defect on a rolling element. In recent years, powerful AI and ML algorithms have been increasingly used for predictive maintenance. When applying AI, two main questions arise: how to represent the data and how to choose the right AI model. There is no single accepted solution, and these choices strongly affect system performance. Data can be represented in three ways: using raw signals, converting signals into image-like forms such as spectrograms, or using handcrafted features. Each has pros and cons, but most successful approaches today use spectrograms or raw signals, which capture rich temporal and spectral information. The choice of an AI model depends on the data and the task. Multi-layer perceptrons work well with feature vectors. Convolutional neural networks handle image-like data, like spectrograms, and recurrent neural networks excel at sequential data with temporal dependencies. Picking the right model is crucial for detecting faults and predicting anomalies reliably. In this tutorial, we introduce the basic concept of predictive maintenance, which is based on continuous monitoring of machine condition using sensors, combined with advanced data processing and AI models to detect faults at an early stage. We discuss the main benefits of predictive maintenance, including significant maintenance cost savings, prevention of catastrophic failures, and sufficient time to plan repairs and procure replacement parts. We also reviewed the techniques used in predictive maintenance, with vibration measurement and analysis being the most common, alongside noise measurement, lubricant oil analysis, performance monitoring, high-frequency ultrasound, and thermography. Finally, we covered vibration measurement in more detail, including acceleration measurement, the operating principle, and basic types of accelerometers, as well as data analysis techniques in the time, frequency, and time-frequency domains, additional methods such as envelope spectrum, cepstrum, and kurtosis, and the application of AI models. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš, and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.